Today we talk about finite set. And previous class we discussed about definition of finite set and some examples, some lemma and consequent theorem, corollary. And today we discuss about one corollary. We start it. Let B non-empty finite set and then the following are equivalent. First B is finite. First is B is finite. And second, there exists a surjective function. There is a surjective function from a section of positive integers onto B. From a section of positive integer onto B. And 3, there is an injective function from B into a section of positive integer. There is an injective function from a section of positive integer from B to a section of positive integer. Sorry, this one is mistake. From B to a section of positive integer. Okay. Then how we prove it? We prove it 1 implies 2. Since B is non-empty, then there is for some n a bijective function. B is finite, that means there is some n, a bijective function if 1 2 n to B. Okay, now we starting on, there is a surjective function, that means 2 implies 3. How we prove it? 2 implies 3. Okay, if 1 to n to be surjective, that means then we define G, B to 1 to n by the equation GB equal to smallest element of F inverse B. GB equal to smallest element of F inverse B. Then because F is surjective, the set F inverse B is non-empty. F surjective, so F inverse B is non-empty. Then F inverse, then Euler-Ordering property of Z plus tells us that, Euler-Ordering property of Z plus tells us that GB is uniquely determined. Okay, then by Euler-Ordering property by OLRRE property GB is uniquely determined. Okay, that means GB is unique. Some smallest element of F inverse B, and if inverse B is non-empty, then smallest element of F inverse B be unique, so GB be unique. Okay, then what we find? We find that the map G is injective. The map G be injective. The map G be injective. Okay, then the map G be injective means for E B not equal to B dash, then the set F inverse B and F inverse B dash are disjoint. Then F inverse B and F inverse B dash are disjoint. So their smallest element must be different. Okay, F inverse B and F dash inverse B dash are disjoint, so smallest element must be different. Now erase this one. So their smallest element must be different. So their smallest element must be different. Okay, next we prove 3 implies 1. Okay, 3 implies 1. If G B to 1 to n is injective, if G B to 1 to n be injective, then changing the range of G gives, then changing the range of G gives a bijection of B with a subset of that, gives a bijection of B with a subset of 1 to n. It follows from the preceding corollary that it follows from above corollary that B is finite. Okay, that means above corollary says that B is finite, then if B to n be bijective, then G B this subset changing range of G, that means some changing gives a bijection of B to, that means B is a subset of A, then changing the range of G, then this one is gives a bijection, because G be a injective function. Injective function means cardinality of b less than n. Okay, then we construct some subset of 1 to dot 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 n, then we find a bijection, and it follows from the above corollary that b is finite. Okay, so next we discuss another corollary about finite set. Finite union and finite Cartesian product of finite set are finite. We discuss about that, so we erase these things. So what we prove? We prove an important corollary. Just b is finite, then there is a surjective function from a section of positive integer to b, and there exists an injective function from b to a section of positive integer. Okay, now we discuss further finite union and finite Cartesian product of finite sets are finite. This one also corollary. Finite union and finite Cartesian product. Cartesian product of finite set are finite. Then how we prove it? First we see that a b finite, two set finite, then show a union b also finite. Okay, this one is trivial. If a b empty, first we show this one. Then if a b equal to phi, then prove is trivial. Okay, now otherwise there are bijection if 1 to dot 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 m to a and g 1 to dot 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 n to b for some choice of m and n, for choice of m and n. Okay, define a function h 1 to dot 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 m plus n to a union b by hi equal to fi for I equal to 1 to dot 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 n and hi equal to gi for I equal to m plus 1 to dot 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 m plus n. Okay, now gi minus m, because here m plus 1, then g1 g2 dot dot gn. Okay, gi minus m, then it is easy to check that hb surjective. Okay, from which it follows then a union b finite. Okay, so a1 a2 dot 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 an b finite, A and B finite. Okay, A1, A2 dot 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 AN are finite. Then union of A1, A2 dot 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 AN are finite. Because A1, A2, A1 union equal to A1 union A2 dot 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 union AN equal to A1 union A2 union AN minus 1 union AN. Okay, then this one finite, so union is finite. Okay, then A B finite and A union B is finite. This implies that finite union of finite set are finite. Okay, this is proved. Now we going to Cartesian product. Finite Cartesian product of finite sets are finite. We have to prove that. So we erase these things. Then we're going to further prove finite Cartesian product of finite set are finite. Now the Cartesian product of two finite sets is finite. First we show that A be finite, then A Cartesian product B be finite. So how we show that? First we take just singleton A and B. That means singleton A Cartesian product B. Okay, this one is finite if we take any element. Then being bijective correspondence with B. Then finite means being bijective correspondence with B. Then the set A Cartesian product B is the union of this set. Is the union of A Cartesian product. So finite union of finite set be finite. Then A Cartesian product B be finite. That is, cardinality of A Cartesian product B is less than infinity. Now we prove if A, we let A Cartesian product dot 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 A n minus 1 be finite and A n be finite, then obviously A1 Cartesian product A2 dot 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 A n minus 1 Cartesian product A n be finite. Okay, so we also show that finite Cartesian product of finite sets are finite. Now we do whole problems on finite set. Now also we discuss if B is not finite and B subset of A, then A is not finite. Okay, how we discuss it? One problem of exercise. we discuss this problem first. This problem says that a subset of B and and A is not finite. A is not finite. This one is given. Okay, we have to show that B is not finite. How we show this one? Okay, A is not finite means A is not finite. Then there does not exist a injective function from A to a section of positive integer. Okay, so this means if a to 1 to n be not injective, this implies if we construct G B to 1 to n, okay, where B subset of where A subset of B or B be the superset of A, then G of A equal to F A belongs to A, and something G of equal to GB where B does not belongs to A. Okay, then each is not injective since FA are the restriction G restriction F, this one is the restriction G restriction A equal to F is not injective. Since this one is not injective, so this thing is not injective, this G is not injective, then we know about that V is not finite. We conclude this. Okay, we prove this one. So simply we prove this one. This problem is done. Okay, so today stop here.